Welcome to the final lecture of Introduction to Symbolic Logic, lecture 15. We are going to do three main things today. First, we are going to learn about quantifier conversion rules. Then we are going to discuss proof strategies for proving quantified sentences. And then in the final part, we are going to look at a few worked examples of proofs that involve quantifiers. So let's start by talking about quantifier conversion rules. Quantifier conversion rules are derived inference rules, meaning that we can prove that these rules are valid using our basic inference rules. We have four different quantifier conversion rules. Each of these rules describes a relationship between existentially quantified sentences and universally quantified sentences. The first quantifier conversion rule allows you to infer that it is not the case that everything is f from the premise that something is not f. So for example, if some apple is not green, the first quantifier conversion rule allows you to infer that it is not the case that every apple is green. Or formally speaking, if there's an x such that not gx, then you can infer that not for all x, gx. The second quantifier conversion rule allows you to infer that everything is not f from the premise that nothing is f. So for example, if nothing is a pair, then everything is not a pair. Or formally speaking, if it is not the case that there is an x such that px, then you can infer that all x are such that not px. The third quantifier conversion rule allows you to infer that nothing is f from the premise that everything is not f. So for example, if everything is not a pair, then nothing is a pair. Or formally speaking, if for all x not px, then it is not the case that there is an x such that px. The fourth quantifier conversion rule allows you to infer that something is not f from the premise that it is not the case that everything is f. So for example, if it is not the case that everything is green, then something is not green. Or formally speaking, if it is not the case that for all x gx, then you can infer that there is an x such that not gx. Quantifier conversion rules are derived inference rules whose general validity we can prove using our basic inference rules. Here I want to illustrate this point using one example. So here I will prove the conclusion that for all x not ax from the premise that there is no x such that ax. And I'm using curly meta variables to indicate that we are here proving the general validity of a form of inference rather than a particular inference. Okay, so I want to prove the sentence for all x not ax. Backward planning suggests to prove this conclusion using universal introduction. Now, in order to be able to prove the sentence using universal introduction, I would need to have a sentence of the form not AC somewhere earlier in my proof where C is a name. Since then I can apply universal introduction to the sentence to infer that for all x not ax. Now our goal has shifted a little bit. Now I want to prove that not AC. And I'm going to use backward planning once again. The main connective here is the negation sign, and backward planning suggests to infer this sentence using negation introduction. And negation introduction requires me to use a subproof that starts with the assumption that AC and ends in bottom. So I need to infer a contradiction from the assumption that AC. Since then I'm able to infer not AC using negation introduction. Okay, so I have two sentences up here at the top of my proof. The first sentence is, it's not the case that there's an x such that ax, and the second sentence is ac. Now, this gives me an idea. If the object C is A, then that means that something is A. And that's going to contradict the sentence in the first line of my proof. So I am going to infer there is an x such that ax using existential introduction applied to line 2. And now I can infer bottom, citing bottom introduction applied to lines 1 and 3. And then I can infer not AC using negation introduction applied to the subproof from 2 to 4. And then I can infer my overall conclusion using universal introduction applied to line 5. Okay, so here we have shown the general validity of inferring that all x not ax from the premise that there is no x such that ax.